All right, so let's look into some, why do I have my headphones again? Let's look into some properties of the big step semantics, right? So we've defined an object which tells us what the semantics of the while language is, but we haven't proved any properties about it, right? So it's only a definition, but it is the specification of the language. So whatever it says is what the while language is. So we're going to prove some properties, and that serves two purposes. First, it's a sanity check, right? Because we know enough about, we have an intuition about the while language that tells us, for example, that it should be deterministic, that when you run the same program over and over, you always get the same result. And also that it doesn't necessarily terminate because you have the while loop. You could have an infinite loop. So we're going to check that. It's a sanity check, and if our definition doesn't pass the check, then we have to fix it. That means there's probably something wrong. There's a bug in what we've written. And it's very easy here to write something wrong. We could just have a prime missing, or an S instead of a T, or an S prime. And second, in general, we have more complicated languages, and we're sometimes not even sure which properties hold or don't hold. And then the proof assistant helps us find that out. So this is one aspect of theorem proving with semantics. Another one is you can take a concrete program. This is the second bullet here. You can take a concrete program and reason and say, okay, if you start in this state, you end up in that state. Or we can start with a symbolic program, where some elements of it are fixed and others are like, oh, this is a variable X, but we don't know which one, or some value E or A. And then we can maybe prove, all programs of this and this shape terminate, and so on. So it's both to reason about the programming language as such and about more or less concrete programs. But we're going to do the former here today. We're going to reason about the language. So this proof is probably the most difficult one in this lecture, the determinism proof. So what we're saying here is assume that starting in a state S, executing big S leads us to L, a state L. So L such as a left, because when I'm going to draw it on the board, I'm going to put it on the left. And then you can also go to R. So you can, starting in the same configuration, you can go either left or right. What we're stating is that left equals right. And here we have two hypotheses on which you can do rule induction. So we're going to arbitrarily choose the left one. And we get 7 goals because there were 7 rules, right? While true, while false, and so on. So we've done a case distinction on the left side, but we're also going to have to do a case distinction on the right side. We're not going to need induction on the right side, but on the left we'll need it for some of the cases. Again, this is a rather difficult proof. This is not a proof, we would not have asked you to do this proof. We're now reviewing it, but this would not have been the homework. We typically ask for simpler proofs, or we ask for similar proofs, right? But now that you've seen one of them, then next time you have to prove determinism, you'll know, oh, okay, the trick is to do an induction on one of the 2 premises, and case split on second. So now you'll know the trick. But if you're not sure, you can always do an induction on everything, and then you end up with lots of cases, and at the end you clean up and you kind of merge the cases that are identical and so on. So okay, we have these 7 cases. So let's start with skip. So what we have here is we must prove that L equals R, and we have the condition here that we start in L, we execute skip, end up in R. And if you remember the rule for skip, it said that the state here and the state there must be the same. So if we do a cases on that assumption, then it vanishes and it actually identifies the 2 variables. And for some reason it prefers R to L. So we have R equals R, and that can be done by REFL. And assignment is the same thing, right? So in essence, if you do 2 assignments and the assignments are the same rule and they're done the same way and they're deterministic, then of course you end up with with the same thing, which looks like this. Okay. Now the more difficult case is, oh no, not yet. Sequential composition is fine. So again, we do case distinction. And here I've renamed some of the variables because, and same here, you know, the default names at some point are just too confusing. So if I remove all of that, and I remove, say, all of this, this is not so bad, but the HR_1 and T1 and so on, I cannot relate to those things. So when looking at a state like this, I'm actually lost. And I could try to spend 15 minutes trying to figure out what goes on, or I can, you know, first rename the variables so that they feel logical, you know, that you have a S goes to T, but S goes to T prime, right? So you have two versions here. So there's a certain, you know, symmetry between the T and the T prime. So my names are chosen so I understand them. This is H. So this is, you start in T, state T. You go to L. You start, say, T prime. You go to R. So this is the non-prime version. This is the prime version. So let's try to write that on the board to understand what happens here, but at least with the good names. All right. So so I'm going to simply write you know, all the possible transitions in some sense, right? So I'm going to draw the states first, right? So this is S. And what other states do we have? We have T and T prime. Right? And then we have from T, we go to L. And from T prime, we go to R. And then we have two induction hypotheses on top of this. So, so these are the states. There are 5 states. I don't know if you can read. I'll try to write bigger next time. And we have these transition here, which I'm going to draw. And then this was following S, this was following S, this was following T, following T. So this is das Haus from Nikolaus. So it's, you see, so the big S's and the big T's are the programs, and then the states are on the edges. And what we have to prove is the equality at the bottom, right? And then once it's written like this, then we have an intuition of what we want to do, which is, you know, we already take one step here. And if the language is deterministic, then those two states should be the same, right? Here in the middle, whoa, whoa, whoa. So that's where we should start. We should try to establish this first. And once we've established this, then again, we're going to diverge from there into two different states. And then again, we're going to say, well, they have to be the same. And you see now this will be manageable because we're going to talk only about S or only about T, not about the whole house, not about S and T. And the induction hypothesis for S will help us here, and the induction hypothesis for T will help us there. That's the thinking, right? So let's see how that pans out in lean. So yeah, so first we wanted the induction hypothesis for S, which tells us, you know, that S is deterministic. You know, deterministic, you know, and not only that, that if you start from S and from big S, small s, you will always end up in state T. That's what this for all R, blah, blah, blah is saying, right? So from big S, small s, from this configuration, you always end up in little t. So that means in particular that this T prime must be equal to this T, because, you know, that must be T. So here we simply take the, you see we need this transition SSR. We need this, to find this as an assumption somewhere, something of that shape. And we have indeed ST prime, right? We want to apply this rule with R being T prime because we want to show that T equals T prime. So that means we need SST prime, which we have, it's here. So we pass HS prime here to the induction hypothesis, and we perform a case on it to because it's an equality at that point, right? So if I say have foo, that will print, right? That will print, you know, this is what we get, t is t prime. Then we do a cases on t prime, and that just replaces all occurrences of, I think, t by t prime, or the opposite. Maybe t prime by t. Let's see. T prime by t, that's better. So that solves the first equation here. All right, so now they're the same. And this is actually t now. And then the question is about here. And well, it's the same story with the program t this time. And then we just have to prove L equals L at the end. We're done. So that's REFL. Okay. So yeah, so the other cases, well, I'm not going to look into all of them, but you see, if then else has a condition. So, so if it's the true cases, then we do a cases on the right side, right? So we have an if then else that is true on the left side, and then we have an if then else that is true or false on the right side when we do a case distinction on it. I mean, it has to be either true or false. It cannot be anything else than if then else syntactically, but that leaves us only two goals. The five others are just eliminated by cases as being syntactically impossible. But we also know that you know, only the true case is possible, right? So we already had B of S, and then we did another case distinction, and we have B of S again. So that's the first case. That makes sense. Whereas here we have a contradiction, right? We're in the false case when we were previously in the true case. So for the case where it's true on both sides, we can use the induction hypothesis in much the same style as we did above. And in the contradiction case, we can use CC. It's very good at finding these contradictions, right? And it continues like this. The while is a bit similar. Now, this is what this was the determinacy, or determinism, I should say, property. What about termination? Well, termination would mean that, you know, for all configuration, big S, small s, there exists a T such that there's a transition. That would mean that from any start configuration, you can always terminate. And if your language is deterministic, that means you will always terminate, because can and will are the same thing when you have no choice. Okay. Well, this turns out to be unprovable, and unfortunately, Lean doesn't have very good support for, say, counterexample generation and such. So you have to figure out by yourself somehow that it's unprovable. You have to think it in your head, or you have to notice as you progress in the proof, you know, why it's unprovable. So this is where Lean doesn't help you much. But what you can do is exhibit a counterexample and prove that counterexample true, right? So show that it is a counterexample. And here what we show, right, is that the program that is a while true loop with an arbitrary body from an arbitrary state will never lead to a state. So it's impossible. So it's impossible that you have a transition like this. And the proof is quite simple. But that's because we're using induction prime. If you were using induction, you would suffer here. But induction prime makes it quite easy. It's like magic. So we start by introducing. I mean, the not is an implication really. So we introduce the positive condition, perform an induction on it, and then there are two cases. The true case has a really weird induction hypothesis here, which is false. Which it's a bit hard to explain, but it has to do with the fact that negation implies false, and you know, everything else is kind of simplified away here. So false implies false. We're in good shape. And in and that was a true case. So let's look at the false case. Well, this time it's not true. implies false, right? It's an impossible case because this loop will never end, so we don't have to worry about exiting this loop. This loop just cannot exit. So that one, you can do it with CC again, or favorite tactic. And finally, we can show some basic properties. They're less spectacular, but basic properties of the rules. So those are a bit more like sanity checks, but they're also convenient. They're inversion rules, right? So we've seen in lecture 5 that whenever you have an inductive predicate, you will often want to have these simplification rules, ideally. So bi-directional inversion rules, at least the ones with implications. And that just makes reasoning easier. For example, when you see this thing here, no matter where it happens in a goal, you can now simplify it to t equals s, right? Otherwise, we could deal with it when it was an assumption of its own. We could do cases and would effectively do the same. But what if we have a very complex formula and this is somewhere deep inside? Then you can, without further ado, simply simplify it. And it's the same with assign here. It's the same with, well, we just did it for everything. If then else, and those are nice little proofs. They're nice little exercises. I think you'll end up having to do, a new language and then prove rules like this for that new language. They're good practice. Pretty straightforward once you get the hang of it, but it's good to develop your theorem proving skills. This is the while. And yeah, I think that's all I will say about them. They're not so spectacular.